Okay. Okay, so we are looking at the RSA scheme. Last time we looked at the textbook RSA, which means that it is not randomized algorithm. So encryption algorithm is using the PK for the message is that M to the E mod N. That's encryption. And decryption is C to the D mod N. So this is deterministic. Then, as I mentioned, this is not going to be secure, right? Because it's attacked. So let's look at how we are attacking this text for RSA. So simple attack on this textbook RSA. Okay. So for instance, so there are two parties like Alice and Bob, or this is web server, and this is client browser. Let's say this is Alice and this is Bob. So they are trying to establish their shared key. So what they are doing is, so for instance, it is sending hello, then it is broadcasting the PK, which is E, N. Then Alice is choosing the some random number, and then encrypting the random using this PK. Okay, so then both party has the same shared key value K. Okay, so in this case, if there is some attacker, eavesdropper, Eve is looking at this encryption algorithm, then how Eve is trying, how break this Eve for this encrypted message. Suppose that K is 64-bit key. Okay, so K is 64-bit. So in this case, you are maybe thinking that if Eve is trying to 2 to the 64 times, then Eve can break it. Right? 2 to the 64 times, then Eve can break the key value K. But actually, with a much smaller number of times, Eve can break these cipher systems. Okay, so let's assume that K is 64-bit. Actually, it should be 2 to the 64-bit. Actually, with less trials, Eve can break it. So Eve can see that the encrypted data, which is K to the E mod N. Okay, so that is available, which is a ciphertext. So ciphertext is K to the E. Okay, let's assume that K is K1 times K2. So even K is randomly chosen, but that K will be composite number, right? So the composite number such that both are less than 2 to the 34. Okay, so definitely if K1, K2 are 2 to the 32, then it's actually dividing these two values, but one value will be a little bit smaller and the other one can be a little bit larger, right? But anyway, the largest one is actually less than 2 to the 34. Okay, so let's assume that this is happening. Actually, we are analyzing the probability of this is happening. Then the probability is like a 20%. So if we are choosing some random number, that random number can be divided into the two numbers, product of two numbers. And one of them is like 2 to the 34. Let's both are 2 to the 34 is likely 20%. Okay, so if you're trying to 5 times, then 1 times you can see this kind of K. Okay, so this is the assumption. So K can be divided into the two numbers, K1, K2, and both are less than 2 to the 34. Then what is happening? Then C is actually K to the E, which is K1 to the E, K2 to the E, and mod N. Okay. Then if we are dividing it, then C over K1E equal K2E mod N. Okay. So now using this fact, what Eve is doing is, Eve first, step 1, Eve is computing all possible case for this left term. So C is given, right? Eve knows the C value. So Eve is trying to C over 1 to the E, C over 2 to the E, C over 3 to the E, C over K1 to the E. Okay. So how many times we have to try? So Eve is making this table. Okay. So constructing these values. So to make this one, Eve has to compute 2 to the 34 times, because K1 is less than 2 to the 34, right? So that's our assumption. So K1 is less than 2 to the 34. So 2 to the 34 times computation, Eve can construct this table value, these values, 2 to the 34 values. Then after constructing this value, then Eve is try K2 to the E. So K2 is from the 1 to the 34. Okay, so Eve is trying to 1 to the E, 2 to the E, 3 to the E, K2 to the E. Okay, so Eve is testing. Okay, so this value is there in the table. Okay, this value is in the table, or this value, or this value, and this value. So Eve is trying to every case. So it takes 2 to the 34 times. For each case, Eve has to look at whether that value is in the table. Okay. So then there is some numbers, right? So maybe like this value, some value, okay. This value is matching this value. All right, this value is matched. What that means? So for instance, this is x to the k. This is c over y to the k. So these are equal. So c over yk is equal to the x to the k. Definitely even know about what's the x and what's the y, right? If it's computing everything. So that means c is x times y. It's not gonna be k. This is e. So k is actually x times y. Okay. So Eve is trying to every case whether that is matched to the c over something to the e. So with 2 to the 34 times, we have to make a table, and we are trying to 2 to the 34 times to check whether this is there. Okay. So checking this value is in the table, we have to do binary search. So binary search doesn't take so much time, right? So for the binary search, we have to, for each number, we have to only 34 times to check. So total time is 2 to the 34, we have 2 times, and then for each case, we have to do 34 times. It's like 2 to the 40. So with the 2 to the 40, if can find the k value. So 2 to the 40 is much smaller than 2 to the 64. Right? So if we are using the textbook RSA, then k should be much larger. Okay? So which means that adversary can break the system a little bit easier. So we have to avoid the textual RSA, which is deterministic algorithm. Okay, so that's the reason why we are using the randomized algorithm. So if we are using the deterministic algorithm, then you can make some, or there are existing some attacks to break the system. Okay, so that's the RSA encryption and decryption schemes. And let's look at how this is going to be actually used in the practical. So, first, let's look at the E value. So E and D and N, right? So E comma N is public key, and private key is D comma N. The relation is E times D mod phi N is 1, right? So phi N is P minus 1 times Q minus 1. Okay. So what's the typical value of E? When we are choosing the E should have inverse in the mode phi N, right? Because E times D should be 1. So that means GCD E comma phi N should be 1, right? So this relation should be satisfied. Instead, E we have to choose. So the smallest E value can be 3, because phi N is P minus 1 times Q minus 1. So P minus 1 is 2 times something, and Q minus 1 is 2 times something. So phi N is including 2 already, because P and Q are prime number. It's an odd number. So E cannot be 2, right? Because phi N is including the 2 as a factor. So E can be 3. But if E is 3 case, what we have to check, phi N doesn't have the factor 3, right? If phi has the factor 3, then it doesn't have a D value. So E equals 3 is the minimum, but in that case, we have to make sure that phi N doesn't have factor 3. Okay, so typically, if, for instance, if E is 3, then what's the encryption algorithm? Encryption is simply M to the E mod N, right? That's the encryption. So M to the cube mod N. So M to the cube is just we need multiplying 2 times, right? M is given, then M squared, M cubed. So we need multiplying 2 times only. So it's very fast. And decryption case, C to the D. So D is generally much larger than E. So it takes a lot of time, but encryption is much faster because we just need to multiply 2 times. But if E is 3, in that case, the n, phi n doesn't have factor 3. So maybe we are trying to a little bit more times to find that n. What is typical E value is, E is, there is the 2 to the 16 plus 1. That is also prime number. So this is prime number. So definitely we have to make sure that E times phi n should be 1. But this is very large number, right? 2 to the 16 plus 1 is very large number. So with a little bit high probability, GCD E comma phi n is 1. Okay, it's very high probability. So this is typically used. This value is typically used. And then how many times we have to multiply to compute encryption in this case? M to the 2 to the 16 plus 1. How many times we have to multiply? To compute this value? So m is given, m to the square, just one time, m by m. M to the 2 times 2 is one time. M to the 2 times 3, which is 2. M to the 2 times 2 square, and m to the 2 times square. M to the 2 times quarter is m cube, m to the cube, right? So similarly, m to the 2 times 16, that's m to the 2 times 15. So how many times we have to multiply? 1, 2, 3, 4, and how many times? 16 times, right? So, and then there is plus 1, so m to the 16 multiply m. One more. So total is 17 times multiplication. So for the encryption, so we just need to 17 times multiplication. Okay. For the decryption, depending on the size of D, right? So D is E inverse mod phi n. So generally the D value is almost same to the phi n. So it's like much larger than value, like 2000 bits. Okay. So if this is 2000, then how many times do we have to multiply to compute to C to the D? Almost, we have to compute 2 times 2000 multiplication. Okay. So decryption is much slower than encryption in RSA. Okay. So RSA case, encryption just we need the 70 times multiplication, but decryption case, it takes like 40,000 multiplication. So it takes a lot of time. So RSA encryption scheme is asymmetric. Asymmetric means the encryption time and decryption times are different. So encryption is fast, but decryption is much slower. Okay, because of number of computations are different. Then maybe you're interested in whether there is some scheme which is providing the same encryption time and decryption time. So there is a encryption scheme that we will learn about that in the next time. Okay. So here RSA case, encryption is fast and decryption is slow. So we'll learn about the Elgamal scheme In that case, the encryption and decryption are almost equivalent. Performance-wise, is equivalent. Okay, and the key length, so like a mod n, size of n, modulus n. It was used 1000 bit for this n. The size of n is 1000, but the secret of this 1000 is almost same to the 80 bit, which means that 2 to the 80 times we can factor for this 1000 bit. Now, what size is used generally? And 2048 bit is used. It's like a 100 bit security. Okay. And 3000 bit, then it is providing 128 bit security, which means 2 to the 128 times security. And like a 256 bit security, much larger bit should be used. Okay. So RSA case, the drawback of RSA is that the key size is large. It's like 1000 bit or 2000 bit. And it's a little bit slow because of the computation. So key size is very large. Like 2000 for n. But actually, for the public case, what's the key size? E comma n, that's the public key size, right? So n is 2048 bit, and E is like a 16 bit, right? Because E is 2 to the 70 plus 1. Okay, so we are finishing the RSS scheme. Any question for the RSS scheme? So to understand the RSA, you have to know about the Euler's theorem, right? So RS scheme is based on the Euler's theorem, which means that m to the phi n mod n is 1. Okay, so using this scheme, we can make a encryption scheme. Okay, so we are continuing about another scheme. So we learn about the RSS scheme now. We will learn about the Diffie-hellman scheme. Let's see. Okay, Diffie-hellman scheme. So let's remind what is the public key encryption scheme. We already know that public key encryption scheme is composed of three parts: key generation, encryption, and decryption. So for the encryption, we are using the public key, and for the decryption, we are using the private key. Okay. So now let's look at what's the Diffie-hellman protocol. So Diffie-hellman protocol is actually key exchange protocol. So using this Diffie-hellman, we can construct shared key between these two parties. So there are two parties, Alice and Bob. So what they are trying to do is they want to construct a shared key K. Okay, so instead of just sending K value from one party to the another party, they are using the Diffie-hellman protocol. Diffie-hellman protocol is based on the discrete log problem. Discrete log problem. Okay. And RSA case, we are using the N, right? We are using the N. N is P times Q. It's two composite number. But Diffie-hellman protocol case, we are just using GP prime. So mode P we will use. Okay. Instead of mode N, we are using the mode P. P is prime number. So that's the difference. What we are assuming is, so we have a G P star. So GP star has a P minus 1 element, right? So every element is relative prime to the P because P is prime number. So this is from 1 to P minus 1. Okay. And among any element, not any element, but there is some element which is generating the all element. Generating means G to the 1, G to the 2, G to the P minus 1 is actually equal to the GP star. Okay. So there is a G, so that G is called generator. Okay. So what we are assuming that GP is given and G is given. Okay. So this is already available. It's publicly available. Okay. Then what Alice is doing is, Alice is generating the public key and private key, right? So using the keygen algorithm, Alice has two generated key. So to generate the key, generation key, Alice is taking random number. Okay. Between 1 to P minus 1. GP star. Okay, so A is actually private key, and public key is, let's say, large A, that is G to the A, or the P. Okay, so private key is A, and public key is large A. Large A is actually G to the A. Similarly, Bob is also same thing. Bob is choosing random number B and computing large B, which is G to the B. And private key is small b, public key is large B, which is G to the B. mod P. Okay. So how they are established the key? Alice is sending the large A, okay, which is G to the A. Then Bob is computing G to the A to the B, right? Because Bob knows about B, so B value. And Bob is sending large B value, which is G to the B. Alice is computing B to the A, which is actually G to the B A mod P, which is G to the A B mod P. Here, G to the A is actually A to the B. Okay, so G to the A B mod P. So both party can compute G to the A B. So this G to the A B is shared key. Okay, so if attacker, eavesdropper, can look at these values, right? This value, G to the A and G to the B, but is it possible to compute G to the AB from these values? What do you think about it? So definitely, if know about A value or B value, then if can compute this G to the AB value, right? A or B is known, then A is known, then G to the B to the A is G to the AB. Where B is known, then G to the A to the B is G to the AB. But if it doesn't know about what's the A or what's the B, is it possible to compute A from G to the A? Can you compute? G is given and G to the A is given, and compute A. What that problem is? What this problem is called? G and G to the A is given, then computing the exponent part. What that problem is called? This is hard, right? It's difficult. That problem is called discrete log problem. Right? So we already assume that discrete log is hard. It takes a lot of times. So this is not going to be possible. So if we cannot extract A value from G to the A or B value from G to the B, okay? So maybe we can think that G to the A and G to the B is given, and computing G to the AB is hard. Actually, this is not really exactly same to the discrete log problem. So G and G to the A and G to the B is given, and computing G to the AB. It is hard. That assumption is called Diffie-hellman assumption. So definitely discrete log is solved. Then Diffie-hellman assumption is also solved, right? This log problem is G to the GA. If we can compute A, then definitely we can compute the AB, right? So the Diffie-hellman assumption is a little bit stronger than discrete log, but still we are believing that Diffie-hellman problem is also difficult to solve. Okay, so Diffie-hellman protocol is based on the Diffie-hellman assumption. So G comma G to the A, G comma G to the B, from those factors G to the A, B is very hard to compute. So this is Diffie-hellman protocol. So let's look at some example then. So everyone can use Alice and Bob, right? Okay. So maybe let's try to define G to the P. So P, let's say P is 17 and generator is, I'm not sure, but it is 3. Okay. So what you have to do is you have to choose some random number and then computing the large A and then post into the chatting window. Can you do it? Okay, I am posting 16. That's 16. How much? 16. So can you post your value? So I'm not telling about the export part. So maybe you can know that G to the something is 16, right? You can find it, but it takes a lot of time. So can you post any value, public value to the chatting window? So you have to choose randomly one value and then compute G to the that value in mode 17. You can use a calculator. Alice, Bob. Alice choosing random number. And to the A. It's given. Bob is choosing B. And computing B. That is given. Bob is computing A to the B. Alice is computing B to the A. That's the shadow key. So I'm sending, which is 16. And you have to choose B and then computing G to the B to me. Then let's try to compute shared key K. Okay. So can you post your result? Anyone? So for instance, B equal 2. Then what's the large B? G to the 2, which is 9. Okay, so you have to post 9. So like this. So any small number B, you have to choose and then compute the exponentiation and post the result into the chat window now. Is there anyone who can compute the PK? Okay, so what you have to do is you have to compute public key in the Diffie-hellman key exchange mode. So how you can compute it? You have to choose some random number, any random number, and then compute G to the B. Okay, so you have to choose any random number, like a number, and then compute G to the B. That to be published. So can you post this B value, large B value? can be b equal 1, small b is 1. 1 is too much trivial. B can be any number. 1 can be possible, actually. But if b equal 1 is chosen, then it is too much easy to guess. B equal A, yeah, that's okay. Small b is from 1 to the 17, 16. So between this number, any number you can choose. You can choose. So then what's the large b, which is to b? So how can you compute 3 to the a mod 17? 3 square is 9. 3q quarter is, how much is it? $13, right? And 8, 3 to the 8 is square mod 17. It is 16. Because 30 mod 17 is equal to the minus 4 mod 17. So 4 times 4 minus 4 times minus 4 is 16. So anyway, this is the correct one. So then what's the large b? 16. If b equal a. Okay. So somebody is posting large b is 16. So then I am posting the 10. Okay. I'm posting the 16. You are posting the 16. So which means the same value are used actually, right? Okay, so then let's look at a little bit easier case. G P star and comma G is given as G 13 star comma 5. Okay. So there are 12 elements, and let's say generator G is 5. Okay. And Alice is choosing a like 3. Okay. Then what's the large A? 5 to the 3 mod 13, which is what? 8. Is it correct? Because 25 mod 13 is minus 1, right? Minus 5 mod 13 is 8. That's correct? No. Yes, no, yes, 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 yes. Yeah, 8. Because we are adding 13, it's 8. Okay, so 3, 8. So it is giving 8. And Bob is choosing B, B as like 2, B. So 5 to the 2 mod 13. Which is, how much is it? 12. So this is going to 12. So then what's the shared key? 12 to the 3. And Bob is computing 8 to the cube. No, not the 8 to the cube, 8 to the square. Right. So this cube here and this in mode 13. What's the value? Right. Why? Because minus 12 is minus 1, right? And what's the 8 to the 2? A square. Is only 12. Okay. The both party has the same value. Mhm. Okay, so then let's look at some another example. GP star comma G is G11, 3. Okay, so then can you compute A and A? And then can you tell me what your A, large A? So you are just choosing random small a and then computing just to the A and then post in the chat. But don't say about the small a. So you have hide the small a, okay? So just tell me the large a only. So can you do it, everyone? After computing this small a and large a, just let me know the large a only. Okay, someone is posting. A is 4. Another one, just say. Someone has 2. Another one. Nine. Okay. Huh? What? What? It's not 2. This is 9. Another one. 5. Just per person, just single thing. So 이외 you are choosing the 5. Okay, Yunan, you are choosing the 9. And is there anyone? Please. You're just choosing number and then compute the exponentiation. So there are only 2%. So anyway, then what's the shared key for both party? Shared key between A and B. So we are the if, so we don't know what's the K value, right? But the 2% can compute. 이외 and Yunan can compute the shared key value. So we don't know what's the key value. Okay, so what's the key? You know? You have to do mode 11. You have to do mode 11. So 25 mode 11, which is 3. And here also 5 to the 2. 3. So both party has the same key value. Okay, I think you need time to exercise the things, right? For this Diffie-hellman protocol, and also you need more practice for the RSA scheme. So I think next time we will do some exercise, like how to generate the key value and then how to do encrypt in the RSA and also Diffie-hellman. Okay. So I think you need more practice. Okay, so yeah, let's see on the Wednesday. Bye.